Hey guys, my name is Pranshu, and
My name is Nikil.
today we'll be presenting a presentation about how to use NVIDIA TensorRT to accelerate the inference of neural networks. Okay, so before we start, let's just go over some of the goals that I have for this talk. And so by the end of this talk, we should be able to understand what is TensorRT and when might we want to use it, how to convert a model in your current framework to TensorRT, what is like the GPU programming paradigm at a high level, and how to use basic CUDA functions using the Python CUDA API in order to implement an inference script that is able to take advantage of TensorRT, how to write a script using PyCUDA and TensorRT to accelerate the inference of your model, and finally, how to do all of this on HAL. So what is TensorRT? TensorRT is a SDK released by NVIDIA that is meant for optimizing and running neural networks on NVIDIA hardware. The way that it works at a high level is that you usually start with a neural network that you've converted into the Open Neural Network Exchange format, or ONNX for short. And at the end, what you would do is you would generate an engine based on the ONNX model, which then you can run using the TensorRT engine that's provided as a part of the SDK. So the way that TensorRT works at high level is that it performs optimizations on your neural networks, such as layer fusion, tensor fusion, kernel audit tuning, quantization, and more. And at a high level, I can explain what those are. So layer fusion is when, if your neural network has layers such as, for example, a convolution layer and a ReLU right adjacent to each other, what TensorRT can do is that it can identify all of those layers automatically without user input and fuse them into one operation, so such that we can reduce the number of computations done during inference. Tensor fusion is when, for example, if you have a tensor representing weights and a tensor representing the bias term, we can combine those at inference time because we don't need them to be separate anymore since we're not doing backpropagation. And that, again, will also save on computation. Kernel audit tuning refers to the fact that GPUs can use multiple different kernels or programs in order to implement common neural network operations such as convolution. Different kernels can be optimized for different sizes of layers and also for different hardware architectures. And so TensorRT takes care of all of this for you by running a bunch of different kernels and identifying the kernels that will be the fastest for each given layer of the model. Finally, you can specify quantization options within TensorRT. So TensorRT supports floating point 16 as a reduced precision format, as well as int 8 with a little bit of more work involved from the user. And yes, you can, so that may be another way that you can squeeze out a little bit of extra performance from the model. And so, like I said, TensorRT allows you to take an your model in an existing framework, such as TensorFlow and PyTorch. Once you have that model in TensorFlow, PyTorch, you would want to convert it into ONNX. And then from ONNX onwards, you can convert it into TensorRT. And usually you can achieve somewhere between a 3 and 5x speed up, although that's highly dependent on the model and the complexity. As a rule of thumb, more complex models generally tend to benefit more from TensorRT, as TensorRT has more opportunities to apply optimizations. And so when might we want to use TensorRT? So first of all, you have to have a trained neural network. If you're still in the process of training your neural network and doing fine tuning and things like that, TensorRT won't be appropriate because you can't convert back from a TensorRT model to a traditional model. As I've said before, TensorRT is great for speeding up inference, reducing latency, and also for reducing GPU memory usage at inference time, which is becoming an increasingly more important use case, with the advent of AI in the cloud and all of that. That way you can have multiple users running inference on one GPU, for example. TensorRT typically has no penalty in model accuracy. Differences between the original model and the TensorRT model are usually less than 10 to the negative 6 or 7 or something like that. And then, of course, in order to use TensorRT, you must have access to NVIDIA GPUs. And like I've said before, you can manually configure characteristics such as the maximum GPU memory usage you want the model to use, as well as different kinds of reduced precision formats that you might want the model to be converted to. And so, TensorRT sounds great and all, but there's actually a couple of times where you may not want to use it. Like I said, if you're still training, then TensorRT is not appropriate at that stage of the process. If you don't have access to NVIDIA hardware, then you won't be able to run TensorRT model because it does not run on CPUs, unfortunately. And finally, if you don't have pseudo privileges during the installation phase, then you won't be able to run TensorRT. Now, fortunately, Dawei has installed TensorRT on all compute nodes for us, and so that won't be a problem for this tutorial. But there are cases such as, for example, if you had a script that you wanted to run Google Colab, even though Google Colab has access to NVIDIA GPUs, since you don't have access to pseudo, you won't be able to install TensorRT on there. I would like to note that you don't need pseudo privileges while running TensorRT. So it's only at the time of installation. And so let's go over a high-level overview of how to convert a model from PyTorch all the way to a TensorRT engine. We'll also go into a more in-depth example of how to do this as well. I think before I start this, I would like to skip ahead a few slides, and then for any of you guys who want to follow the tutorial at home as well, you guys can clone this GitHub repository at the bottom and I'll follow along with the tutorial as well. Okay, so here's kind of like the high-level overview for how to convert your model from your current framework to TensorRT. And so we're going to first start with PyTorch, and then we're going to show an example with TensorFlow as well. And so the first step would be to start a GPU instance on HAL and load the correct module. And so that module is called OpenCE. We'll get into that later. And then we would want to convert that model into an ONNX model by using the function that's already provided within PyTorch and specifying the parameters that I have listed on the slides. If you're looking at the GitHub repository, you can see that there are two files called engine.py and buildengine.py, where you have to specify the specifics of your model architecture in order to generate a model, in order to generate an engine with the correct parameters. And so these specifications would be the input and output dimensions of your neural network, the desired batch size, the maximum GPU memory usage, which is usually just going to be under the amount of VRAM that you have access to on your GPU. And so HAL has 16 gigabyte V100 cards. And so you might want to do something like 10 gigabytes as your maximum GPU VRAM size. And of course, you'd want to set all the correct paths from the ONNX model and also to the destination of where you want the engine to output to. After doing all that, we can run the driver code, which is called buildengine.py, and we'll get into that later. For TensorFlow, the process is much the same. Unfortunately, TensorFlow, as far as I know, doesn't have a built-in function for generating ONNX models, and so we would have to clone a GitHub repository called tf2ONNX, and then there's a command in the README which you can run that will let you convert your TensorFlow model to an ONNX model. One other thing to note is that you must have a model, your TensorFlow model, in the saved model format, which is a little bit more rare. It's not as common as generally you would save your TensorFlow model in an H5 format. There's like a tutorial to convert that tells you how to convert your model into a saved model format if it isn't already. So you would have to follow that tutorial before proceeding with the ONNX step. And again, you would have to modify engine and build engine with the parameters of your model, just like with the PyTorch example. And so I'm going to let Nikil take over. He's going to now go over the Bragg neural network example that is a part of his GitHub that is available at this link here.
Okay, so like Pranshu was saying, TensorRT is used to optimize inference for deep learning models. And today I'll walk you through how to actually do this for a specific model. So the example I'm going to walk through is in the domain of high energy diffraction microscopy, and it's called Bragg NN. Before we jump into that, a few setup steps. So firstly, like Pranshu said, you can follow along by cloning this repository onto HAL. Once you've logged into HAL and cloned the repository, you can activate the environment by running the following. So firstly, you would go into your directory, your working directory, your home directory. And then in order to use TensorRT and PyTorch, we would load OpenCE, which is a module. So here we're going to use OpenCE 1.2.2. That has the versions of TensorRT and PyTorch that we need. And we also need PyCUDA for our inference script. And so this is a one-time installation for you, and you can just run pip install PyCUDA. So now we can jump to the model. So let me give you a high-level overview of what model we're dealing with. So this is in the domain of high-energy diffraction microscopy. Basically, the input to the model is going to be an image like this. It's going to be an 11 by 11 image. And the idea is that the image has a peak location that we would like to determine. So in this case, the peak location is around 6,5 in terms of Euclidean coordinates. And so the job of our model is to take in this image and then output one Euclidean coordinate that says this is the peak location. So the model is predicting these peak locations. So here I have a notebook that I'm going to use to convert this model, which is called zero-centered GPU.pth, into ONNX format. ONNX stands for Open Neural Network Exchange. So it's a format that we will have to convert our model to before we can optimize it for inference. So we start out by setting up our imports, and we load the model. So this is called zero-centered GPU.pth, and we load the state dict for the model. At this point, we want some input that we can feed into the model. So here we just construct an input that we can feed in. You can see that the test input has 11 by 11 as we would like, because it's an image that is 11 by 11. And we set this input tensor up, and this is how the image looks right now. So cell 5 is where we convert this model to ONNX. So what's going on here is we tell, so PyTorch has this torch.onnx functionality, using which you can pass in your input model, which we just loaded. You can pass in an input tensor. This has to be a sample tensor of the size that we would like. This is the output ONNX file that we want to generate. We have to use the appropriate offset version. In this case, we're using 11. And we specify a bunch of other parameters like input names, output names, dynamic axes, and so on. And if we run this command, we will see that in our directory, there is going to be a zero-centered GPU offset 11.onnx file that's saved. So what we have done at this point is to take our pre-trained model, which is called zero-centered GPU.pth, and converted it into an ONNX format. And the purpose of this is to now take this ONNX file and then use it to optimize optimize the inference time. So now we'll actually go more into detail about how this process actually works. So now that we have this ONNX file, how do we actually convert it to an optimized inference engine? And for that, we've set up two files that are convenient to run. These are called engine.py and buildengine.py. So Pranshu will be explaining what goes on in each of these files. So we'll start with engine.py.
Yeah, so first we want to create a module called engine.py, which will then be called by the driver code, which is called buildengine.py. Within engine.py, we can specify parameters such as the maximum batch size, which again is going to be a fixed batch size, which cannot be altered at runtime. And so if you want to create a model with a different batch size, you would have to create a different engine for that purpose. We can specify a bunch of parameters here. For example, the max workspace size, which is the size of the amount of memory that our model can use in bytes. And so here we have it specified to be roughly, I think, either 8 or 16 gigabytes in order to appropriately use up the space available on the V100 cards on HAL. We've also set a flag that allows TensorRT to opportunistically convert some layers into FP16 if it finds that FP16 computation yields a performance speedup. And then we specify some other parameters just to get the input size and to build engine based on that. We define two methods to both save and load an engine. These will be used in the inference script. And I guess at the very top of the file, if, for example, you have multiple GPUs reserved on HAL, you would need to specify the specific GPU that you would want TensorRT to look at. And so we just kind of import OS, and then we set an environment variable to say that the visible device that we want to be looking at is the first visible device, which in this case is 0. And yeah, that is build engine, or that is engine.py. In build engine.py, you would specify the shapes of your model. And so in our case, the shape of our model for the input is going to be 1 by 1 by 11 by 11. And the shape of the output is also going to be 1 by 1 by 11, 11. For the purpose of TensorRT, we've actually chosen a larger batch size. And we found through experimentation that we can run a batch size of up to 16,384 because TensorRT models are more compressed. I'm not exactly sure what the original batch size was in the PyTorch model, but I'm pretty sure that we were able to utilize a larger batch size because the TensorRT model is more compact. And so here we specify some variables denoting the input size. So D0, I believe, is 1, D0 is 11, D2 is 11. And then we specify a shape object in which we're going to pass into the build engine function, which is going to take a look at the O and X path. Then the O and X path represents, of course, the O and X model that we built in the previous step. And we're also going to pass in the shape of the input. And then build engine will build that engine, and then save engine will serialize the engine and save it so that we don't have, so we can use it in our inference script. Okay.
So yeah. That was engine.py and build engine.py. So the idea here is we're taking the original ONNX file and then converting that to an optimized engine. So yeah, Pranshu will now go over some of the PyCUDA details.
Yeah, so before we get into implementing or talking about how would we go about implementing an inference script, I think it's worth taking a couple of minutes to talk about how the GPU programming paradigm works at a high level and how it would work specifically for the purpose of inference. And so generally, if we were just to do inference on a CPU, it would be very straightforward. We would have the full data set on the CPU, and the framework of your choice, TensorFlow or PyTorch, would automatically allocate the appropriate amount of memory for the output of the model. And all you would have to do is call one function called model.predict or something of that nature, and inference will be done for you. With TensorRT, it's a little bit more involved. TensorRT just gives you one function called execute, which takes in input, which represents a single batch of the data, and just spits out an output. And so it's up to you to kind of manage memory between the CPU and GPU and do the appropriate copies between the CPU and GPU in order to actually get the data back. And so on the CPU, what we have is we're going to have the full data set, and we're going to beforehand allocate an array for all the predictions that will then be populated during inference time. We will then use a command called CUDA malloc, which will then allocate the appropriate amount of memory. This is dependent on the data type that we're going to be using. So the precision format, in our case, is going to be FP32, and also the number of, or I guess the size of the flattened 1D array representing the full data set. And so once we allocate that memory on the GPU, we would use a command such as CUDA copy from the host to device to then copy an individual batch from the CPU to GPU. And so now we have one batch on the GPU, and then we would call a command called execute, which is now part of the TensorRT. And what execute will do is it'll perform inference, and it'll save inference on the GPU. And so we would have to call another command called CUDA memcopy from device to host to then copy back that batch back to the CPU and populate that portion of the array. And we would keep doing this over the entire data set. And so we would have a for loop that goes through each and every single batch, does the appropriate memory copies, does inference, and then once that process is done, then we'll have a final array that has all of our predictions. And so I think Nikil can go back to the inference script now, and we can talk about some of the functions that I've just talked about in detail.
Yeah, so we have two inference scripts set up. The first inference script is basically for PyTorch. So it is the traditional model.forward type of script. And then we have another script called TRT for dataset, where we use the engines that we just saw how to build, and we optimize our inference time. I'll start with Torch for dataset. What this file does is basically what we saw in the convert.ipynb notebook. We have a PyTorch model, and here we load the dataset from this .h55 file. We load the model like we saw in the notebook. We set the batch size, and what this part of the code does is it converts, it basically is to deal with batch sizes. So since we're using a batch size of 16,384, but the entire data set contains, it could contain less than 16,384. This part of the code just deals with how to chunk up the data appropriately. So here we run the actual model. And so we initialize an initial empty prediction list. And for every iteration that we run this model, we would just do model.forward. That would run the Bragg-NN model on the specific batch chunk that we have. So this split tensor of J, that refers to one specific batch of inputs. That would be of size 16,384 by 1 by 11 by 11. And having run inference the usual way with PyTorch, we store it in our prediction list. And in the end, we compute things like the L2 norm to verify that our model actually does what we intended to do. So now that we've seen the Torch inference script, we can now describe how we're going to modify this for our TensorRT purpose. Yeah, so I'll first go down to the for loop, and basically here you can see on line 137, instead of model.forward, we have a do inference function. So instead of PyTorch model.forward, we replace it with another function called do inference that basically uses our TensorRT engine to do the inference faster instead of the PyTorch model.forward. So Pranshu will now go over the do inference function and also the various aspects of how we use PyCUDA to optimize inference.
Yep, if you could scroll up to load engine. Yep, that's perfect. Yeah, so the load engine method will let us deserialize a TensorRT engine, and then it'll return an engine. Then we have a method called Allocate Buffers, which will take in an engine, a batch size that we specified, and the data type, which in this case is going to be float 32. It can be whatever precision format you want that is supported by TensorRT. And what Allocate Buffers is going to do is that, as we've described in that GPU programming paradigm slide, we would first need to allocate memory on both the device and the host in order to perform inference. And so we're going to create a page lock buffer so that data can't be swapped into that buffer that's not a part of this function. This will best optimize performance. The buffer will need, in order to specify the size of the buffer, we can simply get the size of the input from the engine by calling the get binding shape property, and we can specify the data type, which will then be multiplied against the size of the 1D array that is returned from get binding shape. So this will allocate memory on the host for the input and output, and the host is the CPU in this case. We then want to allocate memory on the GPU, which should be, again, be the same as the amount of memory that we've allocated on the CPU. And so we can simply just get the number of bytes from the host input and host output. And so we would call memalloc in order to allocate memory in the GPU in order to perform inference. we create a CUDA stream in order to take care of, in order to give us context in which to process the data and perform the correct number of, in order to perform memory copies and mallocs. And then, yes, this is allocate buffers. Load images to buffer. Basically copies the data. What it does is it flattens the data into a 1D array, and then it'll copy it to the page lock buffer that we have on the host. And finally, we have do inference, which will take in a bunch of the parameters that are returned from the previous functions, such as host input, host output, device output, batch size, etc. And it'll load the images to the buffer first, and then it'll create a TensorRT engine. So now we're going away from PyCUDA and now to TensorRT. It'll create a TensorRT engine. If you could just stay and do inference, and then you could maybe have you can start from with engine.create context on line 78. Yeah. So then here we actually perform the inference by doing execute, where we take where we specify the batch size, and we perform inference with the execute function. Then we use memory copy from device to host to get the predictions back from execute. And we do synchronize to make sure that all the processes that are running on the GPU are synchronized. And then now we want to reshape the model or the output back from the 1D array that we flattened it to back into the original data, and back to the original shape that it was in. And then finally we can return. And so do inference will take care of one batch. And as Nikil described earlier, we have a for loop that will iterate over the entire data set and make sure that each batch is processed and the results are copied back to the memory I've allocated on the CPU for predictions.
Yeah. So yeah, that's roughly the idea behind why we're using two scripts. So we want to run the torch for dataset.py that will output the predictions for the PyTorch model, and then we want to run it for TRT for dataset.py that will do it for the TensorRT model, and then that way we can compare the times, the predictions for both of them. So we can actually go ahead and run these files. So let me point out before we run it that for the PyTorch model, we're just using the original pre-trained model, which is called zero-center-gpu.pth. And then for the TensorRT model, we're using this file that we generated. This is a .plan file, and it's the optimized version. So it's got a batch size of 16384. It's FP16, and it uses TensorRT7. So I have a terminal here, and like I described on an earlier slide, you'd have to load OpenCE. So I already have it loaded, but you would basically do module load OpenCE, and the version is 1.2.2 that we're using. So if you run that, you should have that loaded. And then you will also have to do a one-time installation of pip install PyCUDA. So I've already done that here, but if you're starting out with this tutorial for the first time, then you would have to do pip install PyCUDA. So, so now I'm going to run the torch script. So this is called torch for dataset.py, and it uses the original PyTorch model. We run the model for 20 iterations, just so we can get an average time across all the iterations. Sometimes in the first iteration, the model takes longer to get set up. So we want to really run it for multiple iterations and take an average across all of these iterations to really get a good sense of how long it takes. So let me run this now. So what these numbers are, they represent the time taken for every single iteration. So you have 20 of these numbers, and each of those corresponds to the time taken for each of those 20 iterations. And at the end, you can see this is the summary. These are the summary statistics of the predictions. So we essentially calculate the L2 norm. And we can notice here that the 95th percentile, for example, is 0.687. So this is a number that summarizes how close the predictions that the model output are to the ground truth labels. So now if we run ERT for dataset.py, we should see the same 95th percentile. And as you can see, the 95th percentile is essentially the same. It's 0.688. Typically, when you're using TensorRT, you can expect a small loss in accuracy, but in this case, there's essentially no loss in accuracy. And you can see the times that they took. So the PyTorch model took this much time, and the TensorRT model took this much time. Depending on the model you're trying to optimize, you may get a varying, you may get a wide range of speedups. So with some of the applications that we've seen, we've got up to a 5x speedup in our models, but sometimes you might only get like 1.2 or 1.3x speedup in your models. It really depends on the model, but it also depends on the parameters you choose. So for example, with this specific model, if we are currently using a batch size of 16,384, but for example, if we use a batch size of 512, the speedup is much worse than this. So things that you can vary are the batch size and also whether you use FP16, FP32, indate, quantization, and so on. Yeah, so now we have taken a pre-trained model and optimized it using TensorRT. So this is the full cycle of how you would go through this process.
Yeah, and I think that wraps up our presentation pretty much. We can open it up to questions if there are any. If not, thank you so much.
Yeah, thank you very much for this presentation. That's a very useful tutorial. I do have a question. So when you convert models for the inference, do you see any performance losses as a result, or there is no reason for that to happen?
Performance losses in terms of accuracy or in terms of like time taken?
Well, no, in terms of accuracy.
We've never seen any kind of meaningful performance loss in terms of accuracy. Usually the performance is identical, especially if the task is like classification and not predicting like a continuous number or something like that. But yeah, it's very unusual if you see any difference in prediction at all.
Okay.
Yeah, and just to add to that, the official TensorRT website does say the same thing, that the predictions should be identical. But in some applications, you may see a slight decrease in accuracy, for example. In that case, it will still be a small decrease, and in that case, it's essentially a trade-off. So you will have to determine how important it is to you that you increase your speed up as opposed to a small decrease in accuracy.
Yeah, I think that's a pretty sort of usual trade-off. Whenever you have any device that does something different numerically, you can run into that. Yeah. Okay. So another question. So this tool exists purely for NVIDIA GPUs, right? Are you aware of any similar efforts for any other platforms of this nature? Some sort of accelerators that would do a similar work, provide similar framework, similar capability?
Yeah. So there is another similar framework called the Microsoft ONNX runtime, which lets you take an ONNX model and use that as a runtime instead of TensorRT. And this runtime can run on CPUs, GPUs. My understanding is that it can kind of run on virtually any kind of accelerator, I think, that's supported by it. Yeah, so you can always use that. And of course, the tutorial that we've provided shows you how to get an ONNX model out of the framework of your choice. And so you could maybe just even, just look at the first half of the tutorial, get an ONNX model, and then, use this Microsoft ONNX runtime to run on various kinds of hardware.
Yeah, so I actually would say that that's modular what that hardware supports, because we run into this issue of not supporting some layers on Intel's CPUs that use ONNX as a starting point. So I guess is there? Yeah, but that brings up another question. Are there any layers that are not supported in TensorRT, or this is not really even a valid question here because it just uses CUDNN underneath or something like that?
So yeah, it's not an issue with TensorRT. It could be potentially an issue with ONNX. But the thing with ONNX is that they're releasing new offsets all the time. And so in our tutorial, we use like offset 11 or something, but I think they have like up to like offset 15 now, which introduces new neural network layers implemented in them. So it's going to become like less and less of an issue as time goes on.
Okay, makes sense. Okay, if there are no other questions, then thank you very much for providing this tutorial. So we will post the recording, and also if you could please share with us the links to the notebooks so we can also post them there. But yeah, this was very, very informative, very helpful. We are not seeing too many people doing inference per se, but I think that's, that's a matter of time before applications are developed and people have a need to do just purely inference work. And these tools are very, very helpful for this. So thank you for providing this tutorial. I really appreciate it.
Yep, no problem.
All right, that concludes our tutorial then for today. Thank you very much. And so we are basically done with tutorials for this semester. So we will pick them up in the summer, sometimes in the summer.